welcome to what may be the first of many linear algebra videos. In this video, we are talking about vectors. We will specifically be covering the visualization of vector addition and scalar multiplication, which will become sort of the basis for linear algebra. So suppose I ask you to walk 6 feet east and 2 feet north. I can represent that on the xy coordinate plane with an arrow pointing 6 in the x direction and 2 in the y direction, or more formally, what we like to call a vector. And we can name the point that the vector starts at, or where its tip is at. And I'm going to call that point O. Most people call the origin point O, but you can technically call the point whatever you want. And we can name the point where our vector terminates, or the tail of the vector. And I'm going to call it point P, but you can call it whatever you want, with the coordinates 6, 2. And I just got those numbers from the directions that I gave you, 6 feet east and 2 feet north. And those are the coordinates that correspond to it on the graph. And we can name this vector. We can call this vector OP by calling the point where it starts and the point where it terminates, or its tip and tail, and then putting this sort of arrow thing over it. It kind of looks like a regular arrow without the bottom part. So vectors have two qualities, which you might remember from the Despicable Me villain vector, that they have both direction and magnitude. And you might have also heard these terms in a physics class when talking about force or velocity, when there is a size or strength or weight to an object and a direction like up or down or north or south. And then we can also represent these vectors numerically using what are called components. So the components describe in the 2D plane how much your vector goes in the x direction and how much it goes in the y direction. And we would write that like this with a square bracket, and then how much we travel in the x direction, which is 6 units, and how much we travel in the y direction, which is 2 units. In this video, I'm going to represent my components using column vector notation, which is where you write your components stacked like that. But in another class or in other videos, you might see it written as a row vector, where they are next to each other. Or you might see it written with these arrows, 6, 2. And these three notations are all logically equivalent. So the directions to go 6 feet east and 2 feet north are directions that you can follow from anywhere. It doesn't really matter where you start, right? If maybe I want to start from the origin, but you want to start at point, say, 2, 0, are we doing the same thing? Are we both following the directions by traveling 6 feet east and 2 feet north? And the answer you should come to is yes, because we're both going in those directions that I gave. And if that doesn't really make sense, we can actually think of a vector that we have in real life that we're all familiar with, gravity. So even if we're on opposite sides of the Earth, we can imagine gravity as some kind of arrow that is pointing to the center of the Earth, telling us which direction gravity is pulling us and by how much. So we know gravity pulls us down towards the center, and it doesn't even matter if we're on opposite sides of the Earth, we still experience gravity in the same exact way, and it is the same exact vector, -9.81. So we know that if vectors have the same magnitude, which would be the strength, or the numbers, in the same direction, which would be positive or negative, here in our example, we are using a positive direction. We just didn't write the plus signs. But if they have the same magnitude and direction, or the same components, then they are considered the exact same vector. So I want you to take a second to pause and think about what kinds of things we can do with these vectors. Well, one thing we can do is stretch them. If I want to take the vector OP, and I just want to increase it by a factor of 2, just graphically, where does it look like our new vector's tail is? Now, if you've drawn everything proportionally, you should get the coordinate 12, 4. And now we've ended up with this much larger vector. And what does it kind of look like we've done? How does the new tail 12, 4 compare with the old tail 6, 2? It seems like we might have just multiplied the coordinates by 2. And we can show that mathematically if our prediction is that we're just multiplying the vector by 2, you can write that out. Say 2 times 6, 2, which you can just bring the 2 into the vector and have one larger vector, and do 6 comma 2, or 6 times 2, and 2 times 2, bottom. And then it's just regular algebra. 2 times 6 is 12, and 2 times 2 is 4. So it seems like our prediction's right, that if we just multiply the entire vector by 2, or by whatever number you're scaling it by, you end up with the correct tail. And that is referred to as scalar multiplication. Or if you multiply the vector by some scalar, we're just multiplying each of its components by that scalar. So if you have any arbitrary vector with the components a, b, and you're multiplying that whole vector by some scalar c, it's equivalent to just multiplying each component by that scalar. And we can do this with negative numbers too, which you can try to work out on your own. So now we've learned that scalar multiplication is one thing we can do with our vectors. Another thing we can do with our vectors is combine them. So let's say we still have our vector OP, and I want to put a new vector into our plane. We're going to introduce this vector negative 2, 2. I'm going to write the components for it over here, just so we don't forget. Negative 2, 2. And to combine these vectors, I can move this vector, negative 2, 2, anywhere on the plane, right? We talked about that at the beginning of the video, where if I have it here, or down here, or over here, it doesn't really matter where it is. It's the exact same vector as long as I maintain the components negative 2, 2. So I'm going to arrange this vector in a kind of particular way, where I've lined up the tip of my blue vector to the tail of my red vector, and that is called the tip to tail method. So our new combination is now pointing to some coordinate, and graphically we can see that that is the coordinate 4, 4. So I did the red one first and then added the blue one, but what if I want to do the blue one first and then add the red one? My question for you is, do we have a different combination? Well, let's try and visualize it. I encourage you to try doing this by yourself before watching me do it. But we can do the blue vector first, negative 2, 2, and our red vector, which remember had the components 6, 2. We can align the tip of the red vector to the tail of the blue vector. And once you look at that, we're pointing to the same coordinate, 4, 4. So to answer our question of do we have a different combination, the answer is no. We have the same exact combination. And mathematically, we can show this by just adding their components. Right, and we have the first vector with the component 6, 2, and we can add that with the second vector, negative 2, 2. And then you can bring these into one vector and do the math inside one vector, 6 plus negative 2, and 2 plus 2. And that just works like regular addition. We have 4 and 4. And then if we want to do the blue vector first, so negative 2, 2, plus the red vector second, 6, 2, and write that as one vector. Negative 2 plus 6, and 2 plus 2. We get negative 2 plus 6 is 4, and 2 plus 2 is 4. And now we have the exact same vector in the end. And that just shows the commutative property of vector addition. Geometrically over here, it didn't really matter which vector we did first, the red one or the blue one, and we still have the same combination. And mathematically, we showed this by adding their components. It didn't matter which components we added first, the negative 2, 2, or the 6, 2. We still got the same answer in the end. And now that we've talked about scalar multiplication and vector addition, you might be wondering about scalar division and vector subtraction. We actually just learned how to do that, because what is division really? Just multiplying by a fraction. And if we want to divide a number by 5, we could also just say we're multiplying by 1/5. And if we want to subtract a number, we'd also just say we're adding a negative. And if you don't believe me, try it out and leave a comment down below. That's all for this video on vectors. Next time we are going to talk about all the possible ways we can combine vectors, and until then, keep on truckin'.